Okay, we're going to do some problems out of chapter 16. You'll notice right away that this is just basic addition, subtraction, multiplication, and division. There's not much higher level math in this chapter of your book, so it might be a good break if you haven't enjoyed using Mathematica and solving things like the quadratic. So the first problem is on page 672, and it's problem 37. It just asks you to decide what the sign would be for some particular reactions. So we have a mole of solid dissociated, whoops, I have to share the screen. My cat wants in. You can come in. Okay, and then share the screen. Okay, so now you should see the document camera with problem 37, and we have a mole of solid PCl5 going to a mole of PCl3, which is a liquid, and a mole of chlorine gas. So based on what we understand about phases, the entropy should increase going from reactants to products. The second one, we have 3 moles of gas going to a mole of gas and 2 moles of liquid. So we're decreasing the number of moles of gas. So this second one, B, the reaction of methane with oxygen to make CO2 and water, that should have a negative delta S. The next one is 2 solutions, so confined in containers, not free to move about. Even though they're aqueous, the delta S probably will increase because we have a mole of gas on the product side. So we're going from liquid solutions to a mole of gas in pure water. So it probably should have a positive delta S. The next one, 47 on page 673, deals with how entropy changes with temperature and volume. So it just asks you to circle which has the higher entropy per mole. In A, it's ice at -40 or ice at 0. And we know that entropy increases with temperature. There's more energy, more places to put the energy. So ice at 0 is going to be warmer. It's the same phase, but it should have a higher entropy. The next one, I was thinking they meant STP for this chapter, but remember for gases, STP is 0 degrees. So I changed this after I did the second one because it would only make sense. You can't answer it if it's not starting at 0. So nitrogen at STP would be at 0 degrees Celsius and 1 atm. And it's going to nitrogen staying at the same temperature, but the pressure is increasing. So we know if the pressure increases, that the volume goes down. So over here, you'd have the greater volume. So it will have greater entropy. And so C is similar. You start out at 0 degrees STP and 1 atm goes to 0 degrees and 50. So the temperature stays constant, but now it goes to 50 liters. Well, you can't compare atmospheres to liters. So I took the initial sample and used the ideal gas law to figure out what the volume was of the gas here. And this volume was 22 liters. So the correct answer is actually this one that I circled and wrote correct answer in red over here. So nitrogen at 0 degrees and a larger volume, same idea as over here, the entropy should go up. So the next problem deals with the idea of the weight and using Boltzmann's formula for entropy. So you have 3 flasks. They're connected by a volumeless cylinder. And you have molecules that you restrict or allow to flow freely between all 3. Each of those has equal volume, A, B, and C. So they want us to calculate, this is on page 672, calculate the weight and then the entropy. So in the first one, we have 2 molecules and they're in container A. So their number of options for where they can be is just one. They're in container A. But each of them is in container A, and so you multiply or you raise it to the power of the number of molecules you have. So the first molecule can be in A, the second molecule can be in A, so it's 1 times 1, which gives you 1, and the weight therefore is 1, natural log of 1 is 0. So the entropy of that state is 0. If you have 2 molecules randomly distributed between A, B, and C, then there are 3 possibilities. So the number is the number of possible locations for the molecule. And the 2 is how many of them do you have. So each molecule has 3 choices. If you multiply that by the next molecule having 3 choices, you get the total weight for the distribution. So how many total ways could that happen? You could have both of them here, you could have 1 here, 1 here, you could have 1 here, 1 here. So you end up with 9 possible ways to have 2 molecules distributed in 3 flasks. So you end up with entropy equals K ln of 9. Boltzmann's constant is in the back of your book. And the important thing here is to think about the sig figs. 9 is an exact number. There are 9 ways, there aren't 9.0 ways, so this is exact. And if that's an exact number, then we should be limited by Boltzmann's constant sig figs. So take everything that's in the table, and it has 7 sig figs. And so your entropy will be Boltzmann's constant times the natural log of 9, and it will end up with units of joules per K. So this says 3.033598 times 10 to the minus 23 joules per K. So the next one is 3 molecules in A. So there's one way to do it. 3 of them are all doing it that way. So you get 1 cubed, which is 1, and we're back to a situation similar to 2 molecules in A, where the entropy is 0. For D, we have 3 molecules distributed amongst A, B, or C. So just like the situation in B, except we've changed it to 3 molecules. So it's 3 cubed, which is 27. So K ln of 27 is 4.550397. So using the same value for Boltzmann's constant times ln of 27. So 4.550397 joules per K. So E is a mole of molecules all in container A. So 1 place to be raised to Avogadro's number still equals 1 and entropy equals 0. But in F, they ask you, what if you have that same mole, but you allow them to be distributed amongst all 3 containers? So that's the more probable way. So 3 to Avogadro's number is the weight. That's a big number. Not sure your calculator will want to take the natural log. It's easier math if you remember that the natural log of x to the y is y times the natural log. So we can pull Avogadro's number out front times k, and then we just are left with the ln of 3. So Avogadro's number times Boltzmann's constant times the natural log of 3, and I got 9.134381 joules per K. So the difference in entropy between all the molecules ending up in the first container compared to the molecules evenly distributed amongst all the containers would be the entropy of F minus the entropy of E. So F minus E, which is 9.13438 joules per K. So it's much more probable, and therefore the entropy is much higher to have the molecules distributed amongst all the containers. It asks you to use a formula in the textbook and compare. So there's also a formula that says delta S changes when you change volume by this formula, number of moles times the gas constant times the natural log of volume 2 over volume 1. If A, B, and C are all the same size, then you add them together and you get 3 times any one of their volumes. So the ratio of volume 2 to volume 1 is 3 to 1. When I take N times R, we have 1 mole because we have Avogadro's number. So I get just R, and once again, keep all the units from the table because this has infinite sig figs. So 8.314472 joules per K mole times a mole times ln of 3, and I get 9.134381, which is, yes, indeed, exactly the same as using Boltzmann's formula. So I guess the moral of that story really is that an increase of volume is the same thing as saying an increase in the weight, the number of ways molecules can choose to exist. So the next one, 6.55, this is on page 673. So it wants us to use the standard entropy table, so the S naught table, and calculate delta S for these processes at 25 degrees, and then just look at the process and decide why was the sign the way it ended up. So in A, we have solid sulfur, oxygen gas going to sulfur trioxide. I looked up for solid sulfur, 31.8 joules per K mole. Oxygen diatomic gas, 205.1 joules per K mole. So these are all in your table. Sulfur trioxide, 256.6 joules per K mole. So when I take 2 times the product minus, so we have 2 of those, minus 3 times the oxygen and 2 times the sulfur, I end up with a negative 165.4 joules per K. And if you want to think about why it's negative, we go from 3 moles of gas to 2 moles of gas. So that makes sense that the entropy decreases in that process. So for B, we have sulfur trioxide, water forming sulfuric acid. Same process, look each of these up. Notice this doesn't have a sig fig to the right of the decimal, so it's going to change our sig figs. Up here, we knew that when you add, you're limited to the number of sig figs to the right of the decimal, as the smallest number has, so they each have 1 to the right. So this had 1 to the right. Down here, it will be 20 minus 256.6 minus 69.9, and it ends up being negative 306 joules per K. I had to round it because there's no digit to the right of the decimal in this one. So this is also negative. So probably, as we set up here, you have a mole of gas and you have no gas on this side. So it makes sense that you're going from 1 mole of gas to 0 moles of gas. So the entropy should decrease. Okay, 1661. Page 673, if you want to read it. And gives us a reaction. And it gives us the delta H and the delta S in the problem. I didn't even have to look them up. And it wants us to figure out the total change in entropy for the universe when this process takes place. So we know, we want to know it at standard state conditions. So delta S total at standard state conditions will be delta S of the surroundings plus delta S of the system. Delta S of the surroundings, we learned earlier in this chapter, is equal to negative delta H of the system divided by T. So if I look up here, here's my delta H. I multiplied it by 10 to the third, so it'd be in joules, because I noticed this is in joules. So negative 289.0 times 10 to the third divided by 298, and then I need to change that sign, so it ends up being positive. So the delta H is negative. When I change the sign, it becomes positive. And I got 969.8 joules per K. Then for the system, it gave us the number. So where did I multiply it? Oh, I didn't have to multiply. I was thinking of delta G. So Now I have the delta S of the surroundings plus the delta S of the system, which is negative, ends up being positive 800.4, and it still has units of joules per K. Okay, so is that spontaneous? Yes. If the entropy of the universe increases, it's spontaneous. Even though the system itself gained order, doesn't always matter, gave off a lot of heat, so it increased the entropy of the surroundings a lot. So it overcame the fact that the system lost entropy. So, B asks us, at what temperature would it become spontaneous? So I'm going to solve for the point at which we pass through equilibrium to the other side where entropy total is negative. So when it's just zero, it's the delta H of the system divided by T, change the sign so it's positive, and then it's plus the delta S of the system, which is negative, so it ends up being negative 169.4. And then I just have to solve for T. So at what point does it go from being a positive total to the other side where it will become negative? So if I rearrange this and solve for T, I got at a large temperature, which is 1,706 K. Does that make sense? It does not make sense. Let me redo that math. Does not make sense because should be at a lower temperature. What did I do wrong? So let's look back. Because it should be that as the temperature goes down, this has less impact. And as the temperature gets smaller, this has more impact. So how did I? There. Huh. Well, you get the gist of how to do the problem. I'll look back at it and see it does make sense. As the temperature goes down, it should become, oh yeah, as the temperature goes up, it becomes not spontaneous. Yeah, so I'm thinking of it the opposite. So this is correct. As the temperature goes up, then this term becomes more important and it will become less likely that it's spontaneous. So that is the right answer. Okay, so 75 is on page 674. And 75, it gives us the enthalpy of fusion of naphthalene and its melting point, and wants to know the entropy of fusion. So when it says it's the melting point, that means the temperature at which the liquid and the solid are in equilibrium with each other. So we know that means it's when delta G equals 0. So when delta G equals 0, we know delta H has to equal T delta S. We just rearrange this equation, which means if we know we have the enthalpy of fusion, and just look. Oh, this is the entropy of fusion. This is the temperature. So it gave us 128. Should do these the same day that I worked them out because I did these yesterday. So the temperature they gave us is 128. Celsius is the temperature at which delta G equals 0, at which they're in equilibrium. So if you take 128 and add it to 273, you get 401. So 401K times the entropy, which they gave us in the problem, will be equal to the delta H. So the delta H for this process is 19.1 kilojoules per mole. So that's an important concept. Whenever they say something's melting, something's vaporizing, then, and the temperature at which that happens, that's the temperature at which the phases are in equilibrium. So delta G would be equal to 0. So let's look at 85 on page 675. Gives us the reaction. 2 ammonia gas molecules form hydrogen gas and hydrogen liquid. They want us to calculate delta G naught. So delta G when the system has 1 atmosphere pressure for all those gases. So I look in the back of the book, I get the delta G of formation of hydrogen gas is 0. The delta G of liquid hydrazine formation is 149.2. Delta G of formation for ammonia gas is negative 16.5. So I multiply each by their stoichiometric coefficient, 1, 1, and 2. And I get a delta G naught of 182.2. And then the problem asks you, would it help to add a catalyst? So meaning, is it spontaneous and would a catalyst change that? So this is positive, and it's common in thermodynamics to put the sign there even though it's implied so that we know you thought about it. So the delta G is positive. So if all the gases are at 1 atmosphere, this reaction isn't going to happen. So if you add a catalyst, it's going to speed up the fact that it doesn't happen because it will not react forward to make any more product. It's going to react backwards, actually. So adding a catalyst would not help you if you wanted to make the hydrogen. Okay, 2 more problems. 1687 on page 675. And it is giving us this reaction. It wants us to calculate delta G at something other than standard state. Gives us the delta G naught. So that would mean if fluorine gas was at 1 atmosphere, that would be the delta G, but it's not. They tell us that the pressure of fluorine gas is 0.045. So remember when you write the Q, you write products over reactants. Solids and liquids are left out. So the Q is going to be 1 over the pressure of the fluorine cubed. So when I plug that into this equation, I'll have the delta G standard state, RT. So I'm going to use R in joules and then convert it to kilojoules. So I can add it to this kilojoules. And T, it's at 298. Natural log of 1 over the pressure they gave us for fluorine is 0.045 atmospheres. Atmospheres is the right unit to work in. So 1 divided by 0.045 cubed. And I got negative 2045 kilojoules per mole. And yes, that means because it's negative, it is spontaneous. They ask you that at the end of the problem. Okay, 95. 95 is on page 676. So it gives us a reaction, which I've written at the top, ammonia reacting with carbon dioxide to make this guy, which, what is it called? Urea and water. And we want to calculate delta G at different conditions. So in this one, I'm only going to do the first one, but it's an important problem because this is something to pay close attention to. Notice we have gases and we have an aqueous solution. So if we were working in the units for the standard state of each of those, this would be 1 molar, each of these would be 1 atmosphere. If you put ones into Q, natural log of 1 is 0, and delta G would equal delta G naught. That means you have to work in the units that correspond to the standard state of each thing you're talking about. So for the urea, we have to work in units of molarity, and for the gases, we have to work in pressures of atmospheres, which looks very funny to you, but that's the only way it makes sense to talk about natural log of 1 would only be true if you're working in the standard state conditions, and then delta G would be equal to delta G naught. So in order to calculate delta G, we'll take the, did they give us this or did I have to look it up? No, they gave us that. So this was given in the problem for delta G standard state. Add to it RT, ln of, they tell us in the problem that we have 1 molar urea, we have 10 atmospheres of NH3 and 10 atmospheres of CO2. So 1 divided by 10 times 10 cubed, do all of that math, and I got negative 36.4 kilojoules. Let's just think about that for a second. So the gases are the reactants. The product is at its standard state condition. So under standard conditions, this is spontaneous. But if you increase the amount of reactants you have, it becomes even more spontaneous, which is exactly what Le Chatelet's principle would tell us. So it makes total sense that we increased this from their standard state 1 atmosphere and left the product at its standard state. So it's going to become more spontaneous in the forward direction than it was at standard state. One last problem, which is a pretty easy concept. How does this all relate to equilibrium constants? So this is on the same page. And problem 101 gives us the Ka for a weak acid dissociation, which you know a lot about from chapter 14 and 15. And it asks us to determine the value of delta G naught. So delta G equals delta G naught plus RT ln of Q. If we're at equilibrium, delta G is 0 and Q is K. So if you rearrange this, you end up with this equation, which you'll use a lot in your problems. So if you just rearrange this, take this to this side, then delta G naught equals negative RT ln of K. Doesn't matter if it's a KW, a K for an equilibrium of random reaction, or a Ka. The K is related to delta G naught. So negative RT ln of K, and we end up with a delta G naught of plus 20,097 joules per mole. If I round it to the right number of sig figs, it's 20.1 kilojoules per mole. So that will be another common formula that you will use in your homework. So I think that's it for chapter 16 problems. We have 1 chapter left, and you're finished with Chem 108.